we go. Review number 4. John was visiting 3 cities that lie on a coordinate grid at -4, 5, 4, 5, and -3, -4. If he visited all 3 cities and ended where he started, what is the distance he traveled? Okay. So if we look at these 3 points, okay, I'm going to go put these on Desmos to just get a quick picture of the graph. All right. So I'm going to put these, I'm going to actually add these, just add them as separate points. So we've got -4, 5, +4, 5. Type these in. +4, 5. And then one more, -3, -4. All right. So he visited all 3 cities here, and I want to know how far did he travel if he ended up where he started? What is the distance he traveled? So if I was to sketch that shape again, okay, if I kind of look at this, I've got a line across the top that looks straight from -4, 5 over to +4, 5. Then it comes down to -3, -4, and then back up to -4, -5, or -4, 5, something like this. So he goes from this city to this city, and I'm just picking a direction. It doesn't really matter which city he starts in. As long as he goes to all 3 and ends up where he started, then he's good. Okay. So it would have something like this shape. So -4, 5, +4, 5, and -3, -4. So to find the distance he traveled to connect all 3 of these cities, basically, I'm just looking for the perimeter. Now, the top side is pretty easy, okay? If you're going straight sideways, just look at the x values and see how far you traveled. So from -4 to 4, that's a distance of 8. Okay. Now, for the other ones, those are at an angle. So for these 2, I'm going to turn those into like little right triangles and use Pythagorean theorem to find those distances. So let's talk about how far we went up and down on this one on the right. So I had a y value of 5. I went down to a y value of -4. Okay. If I go back to the graph, I could count those. Okay. I could see like just count down lines at a time, 1, 2, 3, 4, and so on. But I want to get to where we can just look at the numbers and think about this. How do you get from +5 to -4? We got to go down 5 just to get to 0. And then you got to go down another 4 to get to -4. So that's 5 and 4. That means 9 is how far I went down. And then look at the x numbers from 4 to -3. Well, go back 4 to get to 0. Go back another 3 to get to -3. 4 and 3 makes 7. So then to get this distance right here on this hypotenuse of the right triangle, we would do the square root of a squared plus b squared. So 7 squared plus 9 squared. That's going to be the square root of 49 plus 81. And that makes 130. So the square root of 130. I could go through and try to list out factors of those, but for right now, I'm just going to leave it as the square root of 130. We won't try to simplify that square root just yet. Now let's go to the other one. So the other one, if I look at the y's, -4 and +5 again, that means once again, the height here is 9. Let me actually switch and write that in blue like I did earlier. And then the x values are -4 and -3. Those are only 1 apart. So then this time when I try to find that distance, it's going to be the square root of a squared plus b squared with 9 squared plus 1 squared, which is 81 plus 1. So we have the square root of 82. Square root of 82. So the 3 numbers on these sides are 8 across the top, square root of 130, and the square root of 82. Now, I don't believe that any of those actually simplify very well, so we're just going to kind of leave it like that. Okay. All right. So that is the total distance he traveled. If they wanted it in decimal form, we could just go type that in. 8 plus the square root of 130 plus the square root of 82, and you get about 19.8. But actually, hang on one second. I typed that in wrong. One weird thing about typing in square roots, if you need to add another square root on, if you just hit plus square root, notice how this is actually typing it under the other square root. That's not what we want. So we have to hit the right arrow to get out from under that first square root, then do plus square root of 82. I thought that was too small. Yeah, then we get 28.4, 0.46, something like that. Okay, moving on to number 2. Triangle ABC is a right triangle. Determine the area. So if it's a right triangle, which angle do you think is the right angle? Hopefully you can look and tell this is the right angle right here. Okay, so 2 ways to do this. We can just find the base and the height of this triangle and do base times height divided by 2. That should work. Or there's a second way where we sort of think of a bigger rectangle that surrounds this triangle and then take away the corner areas, and whatever's left over would be the area of this one. Okay, I'm going to show you both ways here. Let's start with this first way. Because they told us it's a right triangle, we know what the height is, and the base would be the other side. So let's find these. To do this, we're going to use Pythagorean theorem and the distance formula on the side. So this is 2 tall, 3 wide. So the b value would be the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9. That's the square root of 13. That's not a nice value, so we're going to leave it like it is. Then for the height, think of this right triangle right here. It is 1, 2, 3, 4 wide. 1, 2, 3, 4, 5, 6 tall. So that is going to be the square root of 4 squared plus 6 squared, which is the square root of 16 plus 36, which is the square root of 52. Okay. So if I want to find the area, this is going to be base times height divided by 2. So square root of 13 times square root of 52, all divided by 2. Okay. Now, if I know how to simplify square roots, this is actually going to turn out a lot nicer and a lot quicker. But the good news is I can use Desmos here. So I'm going to start by just going right to Desmos and saying the square root of 13 times the square root of 52. And look at that. That makes an actual, a really nice number. And then I'm going to divide that. If I want to divide the whole thing, I can put parentheses around it. But if you're multiplying and then dividing, it doesn't matter if the parentheses around the whole thing or not. Then divide by 2, and look at this. We get an area of exactly 13. So the area equals 13. All right. Now, second way to do that would have been involving one more triangle. Okay. So let's say they didn't tell us it was a right triangle. Then we couldn't assume that the base was this part right here and the height was this other side. Okay, because if it's not a right triangle, then the height is not necessarily one of the sides of the triangle. It could be sort of this other dimension that's a little bit less than one length of the sides or a little bit more than the lengths of the sides. It just gets a little more complicated. So the other part would have been to find the area of this other triangle up here. Okay, this one would be 4 tall and 7 wide. Okay. And what we would have done is we wouldn't have actually used Pythagorean theorem at all. So let me go back and kind of erase the Pythagorean theorem part here and just show you how this would have worked. So what we would have done is found the area of this triangle right here. 2 times 3 is 6. And then divide by 2 because it's a triangle. So we do base times height divided by 2. That means this area is just 3. Then this corner. Base times height divided by 2 would be 6 times 4, which is 24 divided by 2, which is 12. So this area would be 12. And then do it one more time for this big top one. So basically the areas of all these surrounding triangles. So 4 times 7 divided by 2 is 28 divided by 2, which is 14. So 14 is the area of this one. So then the last thing we would do is we would say, okay, the area inside this stuff is like this surrounding rectangle minus all those little triangles. So imagine this rectangle, okay, that like goes all the way around all of that. If I took all of this and then subtracted the three triangles on the outside, the blue, the red, and the black one, whatever's left would go in the green. So how big is this overall rectangle? Well, it's 6 tall from here to here, and it's 7 wide from here to here. So the area of the rectangle is 6 times 7, base times height, or length times width. It's 42. Now let's go take away those surrounding triangles. 42 minus 14 minus 12 and minus 3. What I'm going to do is actually add those three numbers up first and then subtract that total. So 4 and 2 makes 6. 6 plus 3 is 9. 1 and 1 makes 2. So the area of the triangles is 29. So now let's take the rectangle, whoops, which was 42. Take away the area of the triangles, which was 29. And that's going to leave 13. Same area. Okay, so you can think of it as a big rectangle minus surrounding little corner triangles, or use Pythagorean theorem to find the base and the height. If it's a right triangle, and do base times height divided by 2 there. You decide whichever way makes more sense to you. Number 3, identify as precisely as possible the type of quadrilateral ABCD given its vertices at -1, -5, 8, 2, 11, 13, and 2, 6. Okay, let's go type these in, see what they look like. All right, so we've got -1, -5. 8, 2. And I'm going to put some labels with these. So that one's A. I don't know if Desmos will allow you to do this on the test version or not. I don't have the test version open right now. 11, 13 for C. If it does, you can put the labels on. If it doesn't, then don't worry about it. And D is at 2, 6. Okay. So this is the shape we see made. Now, right away, I can tell this is not a square. It is not a rectangle. It looks like it's probably a parallelogram, but I'm not exactly sure. To be a parallelogram, the opposite sides would have to all be parallel with the other opposite sides. So like A to B would have to be parallel to C to D. A to D would have to be parallel with BC. And then if that is true, then we would also check and see how long the sides are, because if the sides are all the same length and it's a parallelogram, then that means it's also considered a rhombus. Okay, so just a quick overview of basic shapes here. Let me just pull this up, kind of basic here. All right, so quadrilaterals, those are 4-sided shapes, right? That's all quadrilateral means, 4 sides. So we have trapezoids. Those are going to be ones that have one set of parallel sides, and then usually the other side is not. They don't have to look like typical trapezoids. They can be flipped upside down. You can have one side that actually has a right angle, but the other side is slanted. That's considered a trapezoid. Okay. Other quadrilaterals are parallelograms, something like this. So this side and this side are parallel to each other. These sides are parallel to each other, okay, but they're not necessarily right angles. The opposite sides are parallel. They're also the same length. If they're all the same length, like let's say, so maybe this is 3, 3, 5, and 5, just making up some numbers. If you have a parallelogram, but all the sides are also the same length, like maybe 4, 4, 4, 4, now that's a rhombus. Okay, so the opposite sides are parallel. All the sides are the same length. That's a rhombus. And then if you start adding in right angles to all the corners, now we're talking about rectangles. And if you have 4 right angles and they're also all the same length, then we're talking about squares, right? And so technically squares are considered a rhombus and a rectangle because all the sides are the same like a rhombus and all the angles are right angles like a rectangle. Both a rhombus and a rectangle are considered parallelograms. Okay, so squares really are rhombuses, they're rectangles, they're parallelograms, they're all of those things. This goes back to that thing you probably heard as a kid, or square is a rectangle, but not all rectangles are squares. There's another shape called a kite. Okay, you can think about it kind of like an actual kite that you see flying. The idea is two sides next to each other are the same length, but that's not necessarily true all the way around. So in other words, these two sides are the same and these two sides are the same, and they connect together, but not the opposite sides. So this one and this one are not the same length. Okay, so that is considered a kite. And these are sort of the basic quadrilaterals you're going to see. So trapezoids with one set of parallel sides, the other sides are not parallel usually. If the sides of the trapezoid are the same, that's considered an isosceles trapezoid, kind of like an isosceles triangle, where two sides are the same length, and then the third side's usually longer or shorter. But yeah, so that's kind of a quick breakdown of quadrilaterals. So how are we going to check and see if this is a parallelogram or a rhombus? We need to know the length of those sides. So let's go back to the data in the problem. So if we go from -1, -5, that was our A point, to 8, 2. Let's see what the Pythagorean theorem says that distance is. Okay. So side to side, if we make a triangle out of this, and it may not be to scale, but side to side, looking at the x's, I'm going from -1 to 8. That's a distance of 9. And then -5 up to 2 is a distance of 7. So this length is going to be the square root of 9 squared, which is 81, plus 7 squared, which is 49. It's the square root of 130. Okay. So A to B, that side length is the square root of 130. Okay, let's go ahead and check and see if the opposite side is the same length. That would be C to D. So its coordinates are 2, 6 and 11, 13. Again, it's not drawn to scale, but let's just see. So looking side to side from 2 to 11, the x values, that's 9. And 6 to 13, that's 7. That's the same length. So that is also going to be the square root of 130. So the opposite sides, AB and CD, are the same length. Now let's check B to C. This one right here. Okay. So from 8 to 11, that's going to be a distance of 3 wide. And then up and down, we're going from 2 to 13, that's 11 tall. So the distance would be the square root of 3 squared plus 11 squared. 3 squared is 9. 11 squared is 121. 9 plus 121 is, look at that, 130. So that's square root of 130. So BC is also square root of 130. And I have a feeling A to D is also going to be that. Let's just check those coordinates real quick. So we went from -1 on the x to +2 on the x. That's a distance of 3. And then up and down, we're going from -5 to +6. That's 11. Yes, this is another 3 and 11 on the sides. So A to D is also square root of 130. Every side is the square root of 130. So that tells me that this must be a rhombus. Okay, I can look at it and visibly tell that they don't make right angles. So it is not a square, but it is going to be a rhombus because all 4 sides are the same. If I wanted to prove that they are not right angles, instead of just saying like, well, they don't look like the right angles. If they were right angles, then these slopes would have to be opposite reciprocals. Okay. And if we look at the slopes of these lines, I want to do this in red. The slope of the top side from C to D, it's going up 7 and over 9. That's a slope of 7/9. 7 over 9, rise over run. Okay. This one on the side here that meets up, so A to D, is rising 11 and running 3. And we can clearly tell that these are not opposite reciprocals. For one, they're both positive, so they're not opposites, because one would need to be positive, one would need to be negative, and they're not reciprocals. 11/3, if I flip that, that's 3/11. That's not the same thing as 7/9. So they're not perpendicular with each other. They're just some other angle. Therefore, it's going to be a rhombus since all four sides are the same. Okay, number 4. This is our endpoint midpoint problems. These go really quick. Line segment GH has an endpoint at 7,3 and a midpoint of 10, -1. So I'm going to put this in a table, X and Y values. And I know the endpoint, I know the midpoint. I need to know what is the other endpoint. We talked about how easy these problems are because it's just find the pattern to get from one end to the middle and repeat it. So how do you get from 3 to -1 in the Y's? You take away 4. So let's repeat that. -1 take away 4 makes -5. How do you get from 7 to 10 in the X? You add 3. So let's repeat that and add 3 again. 10 plus 3 is 13. There you go. 13, -5 would be the coordinates for the other end, which is endpoint H. Okay. Very quick. If you give an endpoint and a midpoint, do that. Now, what if they rewrote this and they said, and an endpoint of 10, -1, what are the coordinates of the midpoint? How would we find the middle if the ones they gave us were the actual ends? Okay. So if that was the case, then what would happen is we could do the same table like so. And we would say, all right, here's my first end and here's my other end. And so they gave us these as our values. All we would do to get the coordinates in the middle is we would average them to find what's right in the middle of 7 and 10 and what's right in the middle of 3 and -1. So to do that with the X's, the X value for the midpoint would be 7 plus 10 divided by 2. That's 17 divided by 2, which is like 8.5. And in fact, 8.5 is right in the middle of 7 and 10. Then do the same thing with the Y's. Take 3 plus -1, or just 3 minus 1, and divide that by 2, which is 2 divided by 2. That's +1. So that would be how we would get the midpoint from two endpoints. Add the X's, divide by 2, add the Y's, divide by 2. And if you're given the end and a midpoint, make that table, find the pattern, repeat it to get the other end like we did before to get 13, -5. All right, number 5. Write the equation of the line perpendicular to y equals 3/2x minus 4 and passing through the point 0, 5. Stop right here. We want to make an equation of a line that's perpendicular to this one right here. Perpendicular to a line means its slope is opposite reciprocal of this slope. Okay, so by opposite, we mean change the sign. This was a positive slope, so we want a negative slope. And then reciprocal means flip it. So we're going to get a slope of -2/3. So if I'm trying to write the equation of this line that is perpendicular to the one they gave me, then I know it's going to start y equals -2/3 x, because the slope has to be -2/3. Then I just need to get the y-intercept. And if we know what's true about all y-intercepts, that their x value equals 0, they already gave us the x-intercept, or excuse me, the y-intercept, because the x value here is 0, so the y-intercept is just 5. So this is going to be +5. -2/3 x plus 5. If they didn't, if it was any other point without an x of 0, then what we could do is go to Desmos, take what we know about the slope, where we know it has to be y equals -2/3 x. Okay, make sure to put the x beside it, not on the bottom beside the 3. And then we would just start picking numbers until it goes through that point that they gave us. So they gave us the point 0, 5. So if I type that point in there, it shows up on my graph. Now I just need to change the y-intercept of my equation that I'm writing until I get that. So let's say I guessed +10. Well, that's too high. So let's pick a smaller one. +8, still too high. +6, still too high. +4, too low. +5, perfect. So I can kind of guess and check until I figure out exactly what it is. Okay, so that's one strategy. Again, that's using Desmos. If you didn't, but you knew the slope was -2/3, this is where you would use point slope form. Remember, y minus y1 equals m times x minus x1. So you would just replace the y1 and x1 with these points. This is your x point. This is your y point. So y minus 5, because that was the y value from the point, equals negative 2/3 times x minus 0. But x minus 0 is just x, so I can get rid of that. And then what I would do is I would add 5 to both sides to get the y by itself. And we get the same equation. Y equals negative 2/3 x plus 5. This is the other way you can do it with any point. It doesn't have to just be the y-intercept. Plug those numbers into point slope form, solve for y, and you're done. So that's it for review number 4. A lot of geometry in this one. If you have questions on that, let me know.